Hello and welcome to another Reigate Maths video, further mechanics, and we're looking at some vector methods that are useful when you are studying oblique collisions. So there's a couple of techniques that we need to think about and have ready to use when necessary. So looking at this, we quite often want to find the component of a vector in a particular direction, and to do that we use the dot product. The explanation for that is quite straightforward really. So suppose I've got a vector u, but I want to find it in this particular direction. Maybe this is the wall and I want to find the component of this vector in the direction of the wall. Now, what we would want to find, if that's the angle theta, we'd want to find mod u, so the size of that vector, times the cos of theta. That's how we would think of it in terms of resolving. But if we look at what we get when we use the dot product, u dot w, using both those as vectors, is mod u, mod w, cos theta. So if we make our wall vector a unit vector, this will be 1, and u dot the unit vector will give us the component in that direction. So that's something that you sometimes need to use, and it's useful to remember it. So if I want the component of u in the direction of a wall, and I know the direction of the wall is 2i plus 5j, then I find the unit vector. So the unit vector would be 1 over root 29 multiplied by 2i plus 5j, and I'm going to find the dot product with 3i plus 4j, and that would give me that value there. So that's the first technique that you occasionally have to use. It's often necessary to find a vector perpendicular to a vector. That's when you know the direction of the wall and you want to find perpendicular to that so you can see where the impulse is going to be. Some people find this very straightforward, some people don't, so it's worth making a point of explaining it. If I've got a wall that has the direction vector 2i plus 5j, then if I want something perpendicular to that, the dot product of that with the initial vector will be 0. So if we think of doing a little dot product, we've got 2, 5 here. I want something that when I do the dot product, it's going to give me 0. So if I switch the values over, 5 and 2, and make one of them minus, that will work, because when I look at the dot product of that, that is 0. So that means that this vector will be perpendicular to this one. So if you switch them over and make one of them negative, it doesn't matter which one you make negative, because that will either give us a vector coming out of the wall or going into the wall, and both of those will do for the calculations we need to do. So that is something that's useful to remember. And the next thing is just looking at what we do, and this is in particular when we have questions where we've got the direction of the wall given as something like this, 2i plus 5j, or we don't have the direction of the wall at all, but we have the velocity before and after, and we need to find the direction of the wall. So what we do is we apply impulses change in momentum, and that gives us the direction of the impulse. And then we can find, once we've got the impulse, we can go perpendicular to that and find the wall vector. We can then use these equations here. And it's worth just learning these really. The second one, this is saying if W is the wall vector, then U dot W is V dot W. This is equivalent to saying that parallel to the wall, the velocity is unchanged. So you can think of U dot W as being resolving parallel to the wall, V dot W resolving parallel to the wall afterwards. Those two will be equal. Now you might say, why aren't we using unit vectors? We don't need to use unit vectors, because if I make this W a unit vector by, say, dividing by root 29, if it was this vector up here, I'd do it on this side as well. So those will simply cancel each other out. So we don't need to bother with the unit vectors, and that makes for neater working. This one here, this is equivalent to E times U equals V, but we've got to take into account the change of direction. So we say minus EU dot I, where I is the impulse direction, is equal to V dot I. So we can then answer the question, might be kinetic energy, it might be an angle of deflection. So let's take a look at the first example. We've got a smooth ball, mass m, moving in the xy plane, and it collides with a smooth fixed vertical wall. The velocity before is 2I plus 7j, and the velocity after is I minus 3j. Find the impulse exerted by the wall on the ball. So this is leading you to help you find the equation of the wall, because we don't know which way, where the wall is at the moment. We don't know what angle the wall is making. So let's have a look at what we do. We're going to say impulse equals change in momentum. Change in momentum. So impulse is going to be the mass, which we don't know, won't matter in a moment. The change in momentum, well, the velocity after is 1 minus 3. Take away the velocity before, or the momentum before rather, is 2, 7. And so when I work that out, I'm going to get m times minus 1 minus 10. So the impulse, is m times minus 1 minus 10, and that would be our answer there. Just check that it doesn't ask for the magnitude of the impulse. No, it wants the impulse, so we give it as a vector like that. This is telling us that the impulse direction is minus 1 minus 10. Now we also need to know the direction of the wall. So if the impulse direction is minus 1 minus 10, the wall will be perpendicular to that. So we can say that the wall direction will be, switch them over and change the sign. So that's the wall direction there. And let's just check, if we did the dot product, it would be 0. Now it says use the scalar product to find the coefficient of restitution. So what we're going to use is this equation here that says minus E times by U I, and this is a vector parallel to the impulse direction multiplied by the initial velocity, or dot product with the initial velocity, is V dot I. Each time you do these questions, write that out, because you're not given that in the form of the book, and so you need to be able to remember it. So let's see what we do here. We get, we're trying to find the coefficient of restitution. So I've got minus E. The initial velocity is 2,7. The impulse direction is minus 1 minus 10. And that's equal to the final velocity, which is 1 minus 3, multiplied by dot product, minus 1 minus 10. So working this out, I get minus E, and then what have I got here? Minus 2, minus 70, so that's times minus 72, is equal to, this is minus 1, plus 30 is 29. So that gives me E is equal to 29 over 72. So in this question, we didn't actually need to use the component parallel or the vector parallel to the wall, but you do sometimes need to find that. So you must be able to do both of these things. You can see here how much simpler it is if we can use these vector methods. It would be possible to solve this question, drawing out the diagram, finding these velocities, finding these as speeds, then finding the angles, but it's very much harder work to do that. Let's look at the second question. So this time we know the mass of the ball, it's moving the XY plane and it collides with a smooth fixed wall which contains the line x plus y equals 3. So this is giving us the equation of the wall. So if I draw out a diagram to represent this, so I've got x plus y equals 3, something like that, and just before impact, it's -4, -2. Again, just have a little look at what that looks like. So -4, -2. So that's going to be coming in something like that. Okay, and that's u is -4i -2j. And then there's going to be a rebound like this. And we've got to find that. So I'm going to call that xi plus yj. So I've now got my diagram. I know that the wall vector, so parallel to the wall, well, this has a gradient of 1, so it's -1, 1. Or we could say 1, -1. 1 minus 1. So parallel to the wall is 1 minus 1. So perpendicular to the wall, which will be the impulse, we need to switch those over and make one of them negative. So we can have -1, -1, but we can also have 1, 1, because we just need a vector perpendicular to the wall. It doesn't actually matter whether it's coming out of the wall this way or that way. So that is the one I'm going to choose here to use this one, because we don't want to use negatives if we don't have to. So I've now set everything up like this. I'm now going to look parallel to the wall. So remember, this is really just applying the methods we applied before. We're going to go parallel to the wall and perpendicular to the wall. So parallel to the wall, things are unchanged. So we've got -4, -2, dot 1 minus 1 is equal to 1 minus 1 times x dot xy. So this is going to give us -4 plus 2, which is -2, is equal to x minus y. And that's equation 1. And you can see what's coming. We're going to look perpendicular to the wall, and that's going to give us some another equation. So let's look perpendicular to the wall, and that's in the direction of the impulse. Direction of the impulse. So in the direction of the impulse, we've got -e u dot I equals v dot I. So make sure you are learning this formula, because this is very important to be able to remember that. We're told that the coefficient of restitution is 1/2. So I've got -1/2. My initial velocity is -4, -2. The impulse direction is 1, 1. And that is equal to the final velocity, which is xy, and my impulse direction is 1, 1. So working these out, here I've got, so this is -4, -6, multiplied by -1/2 gives me 3, equals x plus y. And that's equation 2. So equation 1 and equation 2, if we add those together, so equation 1 plus equation 2, I'm going to get 1 is equal to 2x. So x is equal to 1/2. And if x is equal to 1/2, y is equal to 5/2. Now, the question has given you velocities in terms of i's and j's. So we need to give our answer in terms of i's and j's. It's absolutely fine to work in column vectors, and probably in the exam you would be all right if you gave your answer as a column vector, but just to be absolutely sure, I would say velocity after impact is a half I plus 5/2j. And just check you're finding the velocity and not the speed. Obviously, if we needed the speed, we would square and add and square root the components. So those are some useful vector methods. I would say if the question is given all in vectors, you're going to be using some of these methods. If it's given in terms of actual numbers for the speed and degrees for the angles, then you would use the methods we used in the previous section.